Alright, so we've talked about the quantization. So if we use, let's say, the compact IIR, it means, or the LM35, if we use the LM35 sensor, it means we won't get 0 to 40. We will get 0 to 0.4. So if the amplitude here, if we make it 0 to 0.2 with an offset of 0.2, it means we're going to go now from 0 to 0.4. So this is theoretically what we'll get. We won't get, as I say, you never get your sensor in degrees Celsius. You'll get it in voltage, and you have to calibrate it to be in voltage. The noise won't not be that big. Let's just make this amplitude of 1, which is really big, in this case 0.1. Again, I'm simulating the signal. You will get this type of signal from your sensor itself, and it might look like noisy like that, but it's going to look like this. So let's just make that 1 now. I don't know what the range is for the gain. We'll just see here what's going to happen. It goes from 0 to 4.5 almost. So we'll just make it 0 to 5. So our input range, as you can see, there it goes from 0 to 40 degrees Celsius, but it's very noisy. This one is smoother, but it's not calibrated, so we have to calibrate it still. I'm just going to do a quick calibration. It's not the right way. You'll have to calibrate it using an actual value. So you'll put the 40 degrees there, see how much you're reading here, and then multiply with that constant. But I'm just going to cheat a bit. I'm going to get the calculation for the maximum value. Let me just go to numeric. Sorry, just array maximum and minimum. Just going to get the maximum out of that, because the maximum value is supposed to be my maximum temperature. Create indicator. As I'm saying, I'm cheating a bit. You're supposed to calibrate it. And create indicator. So if we run it now, we will see that 0.5, the value 0.5, we're getting 0.5, that's because of the noise as well, is giving us a value here of 4.6 roughly, 4.5. So if we then use the calculator, just to see what we need to divide with, 4.5 divided by 0.5 gives us 9, so we have to divide by 9. So if I go then here, I put my calibration factor in here, multiply. And remember, we've talked about preamps as well. If you use a non-inverting preamplifier, this value might change. Create constant, 0.9. Sorry, 1 divided by, if we do it the other way around, 0.5, 0.5 divided by 4.5. 4.5 times 11111. And then this one is normally the capital K, they call it the calibration coefficient, capital K. If we run now, we just calibrate this one, also to 1. We can now see there's our noisy needle, there's our smoother needle, so it's a better control circuit measuring. We're still not at 0.4, we can still calibrate it to 0.4, adjusting that value until we get 40 degrees Celsius, as I said in the beginning. But this is just a nice indication at the moment. So the calibration would be done depending on what the gain is of your preamplifier, depending on what your sensors is, but that would be that. Sometimes it's not a linear sensor, then you have to not multiply it with a straight value. It's going to be whatever your transfer function for your linear function is. So you can see now it's this. Again, if you want this in degrees Celsius, we still have to multiply this with 100. So if you want that one not to show 0.5 or 0.4, means if we multiply this with 100 and that calibration factor, and we change this to let's say 100 degrees Celsius, then it's going to run from, oh, I've done too much, sorry, 10. There we go, sorry, not 110. See, now this is in degrees Celsius, so I've calibrated that to show in degrees Celsius. Alright, the next video I'm going to show you how to do this on a my Rio with the FPGA.